live. We're going live. Okay, I understand that we are live. Yes, so hello everyone and welcome back to the Latin America webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar number 158, and we're having Aurélien Martens as a speaker. Aurélien finished his PhD at LHCb in 2011, carried out at Université Paris-Sud 11, which is now merged into Paris-Saclay. This was then followed by a postdoc at Université Paris 6, which is now merged into Paris-Sorbonne, after which he decided to move towards optical systems in accelerators. Thus, in 2013, he joined LAL, which is now called IJCLab, right? And now works in quantum backscattering and its applications for high-energy colliders. So today, Aurélien will give us details on the challenges that must be faced in front of the construction of the electron-positron future circular collider, right? Now called FCCee, but we'll see how it's rebranded in the future. We are very happy to have him as a speaker today. So before we begin, let me remind the viewers that you can ask questions and make comments via the YouTube live chat system. And these questions will be passed on to Aurélien at the end of his talk. So we're all yours.
Thank you very much, Joel, for this very nice introduction to the topic of that I like, which is the energy calibration at FCCee, and I will discuss this right after. I'm just trying to share my presentation now. Okay, you should now see the first slide of this presentation. So,
Yes.
as Joel mentioned, I'm working. I'm sorry, I'm trying to remove. Yes. I'm working for the FCCee project, which is the Future Circular Collider for Electrons and Positrons, which is meant to be constructed and installed in the Geneva area where the LHC is currently running. So I said I'm working with the Université Paris-Saclay, and my member institute is CNRS, which is the French National Institute for Research, in particular covering particle physics and related topics. So, yeah, yes, okay. So why FCCee? And I just don't want to go into the details, but I just decided to start with a simple example. I think it's a quite remarkable example where the need of a precision experiment gets clear. So on the plot that you have here, you have in blue the fit of standard model observables, excluding the measurements of the W and the top mass. While in green, you have the current measurements of direct measurements of the W and top masses from both E+ E- colliders and hadronic colliders as those at the LHC and the Tevatron. And both measurements look compatible, as you can see, of the overlap of the green and the blue shaded areas. But recently, there was a very much more precise measurement of the W mass that was published by the CDF experiments, which was not included in the plot that is initially from the publications that are in a reference here in this slide. And so this measurement is about a factor 2 to 3 better than all the previous measurements, and is shown in this red line shaded area on the plot. And you can see that you start to observe some sort of a tension in between this direct measurements and the fit of the standard model observables, which brings out a new puzzle to be solved in the coming years. And so this puzzle can be solved in two ways. Maybe the fastest way, the obvious way, is to try to make similar measurements with the LHC experiments. But there is also another way to proceed, is to build a new E plus and minus collider, increase precision in W mass by not just a factor 2, but an order of magnitude, and at the same time also measure all the other standard model observables, electroweak observables, with much more precision. So you will shrink all the ellipses that are shown on this plot and all the lines that are shown on this plot. I should also mention that the measurements made by the CDF experiments partly relies on a very precise momentum scale calibration that is using actually a mass candle, which is the JPSI particle. And actually, the measurement of the mass of the JPSI has been done in Russia, in KADR, in Novosibirsk, using very accurate calibration of accelerators' beam energies. And actually, they were able to calibrate this with 2 ppm, so 2 parts per million, 2 to the minus 6 accuracy, which is really impressive. And actually, measuring this W mass, for instance, at a new E plus and minus collider with very high precision would use very similar techniques to those that have been used in this Novosibirsk experiment. So we'll try to, I will try to expose you quickly what is FCCee, what are some of its objectives. I won't go into too much detail or the whole physics program of this FCCee. And then I will try to explain you how challenging is the measurements of the energy of the beams and the energy of the center of mass of these colliders experiments. And we finally wrap up. So FCCee, in a nutshell, is actually a project that encompasses both an E plus E minus collider, which tries to test the intensity frontier, so increasing the luminosity of the collider by orders of magnitude to the previous generation of the LEP that was installed at CERN, the Large Electron Positron Collider in the 90s. And so this will be a first step for this project, where we'll try to produce with copious amounts of Z's, W's, Higgs bosons, and top pairs. And the goal is to install the machine and operate experiments in between 2045 to 2060. This will be a 91 kilometer circumference new accelerator, which will reuse most of the CERN infrastructure and will share civil engineering and technical infrastructure with a next generation Hadron Collider, which would be able to reach 1 TeV center of mass energy, so slightly less than an order of magnitude more than what is currently reached at the LHC. And the goal for this second accelerator in the same tunnel as the FCCee would be to operate experiments in the last decades of the 21st century. I should also note that there is a similar project proposed in China, which is called CPCS-PPC. The challenges are very similar, so I will concentrate on FCCee, which I'm working on. You should also know that there are several linear colliders projects, ILC, CLIC, for instance, that were proposed since decades and which would cover parts of the physics program of this FCCee, and with some differences. And there is also a muon collider that is also under study. I will not cover those other projects furthermore. The FCC tunnel, so I said, is about 91 kilometer circumference. Mostly, it's planned to be mostly drilled in the molasse, which is a soft rock, which would reduce the cost of the tunnel building. A small part will be in the limestone, which will be a more difficult place to drill, and we'll have 8 surface sits. and some very very deep shafts, about 600 meters at, for instance, the point F here shown in the plot, which is one of the deepest shafts for such a machine. Maybe you know that LHC the shafts are deep about 100 to 200 meters currently. So this will be also a challenge to face in terms of civil engineering and so on for the FCCE and the FCCee tunnel. If we look at the performance of the FCCE very quickly, we see here a table that summarizes many parameters of the machine. I will not comment all of them. I will start with the first line. Of course, this is the energy, the center of mass energy. Sorry, the beam energy, not the center of mass energy, the beam energy used for the production of these, the W pairs, extra long, and TT bar. Beam current is in the range of 1 ampere at the Z, with a large number of bunches, a large intensity per bunch. All those numbers have been optimized also in terms of the amount of the synchrotron radiation loss that is generated by these beams circulating in the collider. One important thing to note is that here the machine has been optimized to have very, very low vertical emittance, so that the beams will be actually flat at the collision point. As you can see in violet here, the numbers enlightened shows that the vertical beam size at the interaction point of the experiments will be a few tenths nanometer for an horizontal size of a few micrometers, a few micrometers to a few tenths of micrometers at the TT bar threshold. Another point important to note is that the bunch length of the beams will be modified by the fact that the beam interacts with, for instance, the electron beam interacts with the positron beam. So seeing the opposite charge beam at the interaction point enlarges spreads actually the energy of the beam and spreads the length of the beam. This is a very important effect, which means that actually the energy spread of the beam will be relatively large. We'll see why it's important to keep this in mind later. And the luminosity that is targeted by the FCCE at the Z is in the range of 10 to the 36 per centimeter square per second, which is the record of luminosity that would be reached in such a collider. The total integrated luminosity will be large. In 4 years, we expect to collect 5 10 to the 12 Z bosons, which is 5 orders of magnitude larger than what was collected at the Large Electron Positron Collider at LAP in the 90s. It would also allow to collect W pairs with orders of magnitude more copious amounts compared to LAP times. We would be able to collect 10 to the 6 Higgs's and 10 to the 6 top pair pairs. Sorry. And this is assuming 4 interaction points, which would also allow for independent cross-check, especially at the Z, where a very high precision on the electroweak observables is targeted. It would also allow to improve on the planned belt integrated luminosity by a factor about 10, which would allow to trigger precise B bottom charm and tau physics, and also try to look for very, very rare processes that cannot be searched for at BER2, for instance. So if we picture in a plot where lies the FCCE in a plot that shows the luminosity here in the vertical axis versus the center of mass energy of the collider in the horizontal axis, we see that FCCE lies in the very top region of this curve. And you can compare here, so on the around 100 GeV on the top, the red dot is the FCCE and the Z mode. This is a design value. You see it compares slightly to the current design for the Super KGB, which is delivering luminosity to the Bell-2 experiment in Japan, in Tsukuba. And you see that it is orders of magnitude larger than what was obtained at the lab in the 90s at CERN. And this is where the improvements lies, and this is why the very high statistics and very high precision of electroweak observables can be reached at FCCE. We should also realize that Super KGB nowadays does not operate quite to the design. Only a fraction of the instantaneous luminosity has been reached at Super KGB. And actually, Super KGB is an upgrade of the KGB accelerator that you see on the red dot that is encircled by this red line, and actually the luminosity is progressively increasing towards this green dot, which is another adventure that I will not go too much into detail, but maybe one slide about it, because this is a very excellent testbed for the FCCE and the challenges that will lie at FCCE in terms of accelerator technology. So Super KGB that is sketched here is a double ring accelerator. You see here a LINAC. I hope you see my mouse. You have a LINAC that is then injected in the ring that is shown here in yellow, and positrons are created actually somewhere here in a target, and then injected in damping ring to improve to stack positrons, and also to improve the emittance of the positron beam, and then injected also in the counter-propagating ring with the collisions taking place in this region here where the Bell-2 detector is sketched. This is currently the place where the world record has been reached in terms of luminosity, but also in terms of beam focusing. So if you look at the formula that is on the slide here, you have the vertical beam size, RMS beam size, which reads at the square root of product of two functions: the emittance, which actually encompasses information about the beam quality, and another parameter, which is the beta tone function, beta, which actually is related to the magnetic arrangement of the accelerator. So this is design, and this is what we call beam focusing. So reducing the vertical beam size to increase the luminosity induces either improving the beam quality and reducing the beta function or the beam focusing, improving the beam focusing. And actually, Super KGB is has reached recently a slightly less than 1 millimeter beam focusing, 0.8 millimeter, which is in the ballpark of the design of the FCCE, which shows that actually this is possible to do so. You should also realize that increasing the beam focusing means that you have a more divergent beam. So this means that somewhere close to the interaction point, you also have a large beam that you have to manage and ensure not to lose in the accelerator. So this is also why it's very challenging, and this may also induce large backgrounds and so on. So this is also a matter of worry for the detectors. So besides physics and besides all the potential of Bell-2 and Super KGB, this is, as I said, a very good test bed for the accelerator development for the FCCE, and already shows a very good performance and is improving. And actually, it's restarting this week, or last week it restarted, and progressing on improving the luminosity. So let's go back to FCCE and try to sketch the physics scope in a couple of slides. As I said, there will be a copious production of Z bosons, which allow Z-line shape studies, flavor studies, rare decay studies, studies for the dark sector, and also QCD. To W pair production, which will allow a very precise W mass and width measurements, and also test of flavor, for instance, a very precise VCB measurement. Copious production of X bosons, in the IJCLab process, so in conjunction with Z boson, which will allow to measure X couplings with a very high precision, a few percent typically, and also the cross-section for this IJCLab process, and also top pair production, which will allow top mass measurements and couplings of the top, and also vector boson fusion process for the X. And of course, all of this data will provide indirect sensitivity to new physics at much higher energy by very precise electric observable measurements. There is also a possibility to extend the program beyond that was initially planned. This has been realized in the past years. For instance, QCD precision studies by going to lower energy center of mass energy, running at the Higgs, the 125 GeV energy would allow precise electron Yukawa measurements, well, at least the measurement of the electron Yukawa, and also more precision Higgs mass measurements running at 220 GeV. For all these measurements, Z-line shape, W mass, top mass, Higgs mass measurements, a knowledge of the center of mass energy is absolutely essential, of course. And I will just try to make it clear very quickly. I'll just take two examples. On the left here, you will see the Z line shape. So this is a Z resonance scan that has been made at the lab time. And you see here the LF, Delphi, F3, and Opal experiments of the lab. And the dots show the measurements, and the green line, the fit of this Z line shape. And in the dotted dash line, the corrected for QED effects, corrected Z line shape for QED. And so you see clearly that having a very precise measurement of the beam energy is essential to place properly the points on this curve and to be able to fit precisely the Z mass and the Z width. Similarly, you see on the right-hand side of this slide, a scan around the W pair production threshold, so around 160 GeV. And you see a nominal curve in red for a given W mass and width. And you see that the change of the W mass corresponds to the orange area, while a change in the W width corresponds to the green area, which shows that a fit of the cross section for W pair production around the threshold is sensitive with good precision to W mass and W width, as long as you're able to properly place points in these curves, knowing the center of mass energy, which is the horizontal axis here. If we go a bit further in the details for the Z, this is again just an example on the Z, because most of the work has been done for that so far. You see that with the planned integrated luminosity for the FCCee, the statistical precision on the Z mass and the Z widths is expected to be of the order of a few keV, 4 keV. While the knowledge on the center of mass energy at the time of the study that has been made in the 2019 was expected to be in the range of 100 keV, so the absolute scale. But then, for instance, for the Z width measurements, what is more important is the point-to-point systematic. So changing the energy from one point to another, controlling possibly changes in the bias of the measurement of the energy, or possibly the changes in the center of mass energy. And so this point-to-point systematic uncertainty is expected to be in the range of 40 keV, which will turn out as systematic uncertainty of 22 keV, for instance, on the Z width measurements. So these are just two examples. Of course, you can do this work for other electroweak observables. But it shows that you need a very high reproducibility in the measurements of center of mass energy and at various center of mass energies. And so for that, we'll use two tools. One which consists in extracting as much as information as you can from the physics experiments themselves. So using, for instance, mu plus, mu minus pair production in the experiments, in the 4 experiments that will be at the FCCee, to calibrate crossing angle, luminosity, and spread in center of mass energies. And at the same time, having beam-based measurements in the real time, so a measurement of the beam's energies, so the positron beam and the electron beam in real time, and combining those two informations, well, it's more than two informations, but all these informations, then you're able to reach the precisions that have been listed here. And maybe you could even do better by improving your models and your understanding of your machine. So I will try to navigate into this program of measurements, and we'll also be able to calibrate the center of mass energy at higher energies than the Z and the W pair. But before that, just want to picture the legacy that left us people that worked at who worked at the lab. So on the top plot, you see change of beam energies as a function of time. So this is time in hours. For the data that has been taken on this 11th of November, 92. Green dots with yellow bars are measurements of the beam energy that were made with the similar technique that I will describe later on. And on the red, this is a model of tidal effects, and you see that both fit reasonably well. But you see that the scale of the change of the energy over a day is typically of 10 mega electron volts peak. Okay, and if you come back to the previous slide, remember that we want to measure Z with a 4 keV statistical precision, and we target to have better than 100 keV systematic uncertainty on the absolute energy scale at the center of mass energy. So you see already that you have to really control in detail those tidal effects and model them very precisely. Unfortunately, this is not the end of the story, or this is what makes it even more interesting. It was realized at the late time that tidal effects could not explain all the change of energies. And they realized that they were also observing leakage currents circulating into the lab, into rivers, La Versoix, close to that was circulating close to the lab, and the train lines, so the TGV line, deserving Geneva from Paris, that is also passing by lab. And these leakage currents induced a change of the magnetic fields in the machine that are powered up with electrical powers, and a change of the circumference in turn, and then a change of the energy of the beam. And so all these effects, small effects, have to be controlled to very high precision to be able to do a very precise measurement of the beam energy. So this is not a very simple task. And to finish on that, unfortunately, the lab was not designed and was not thought to be able to measure those beam energies very frequently. And so it was basically done only once a week at the lab time. And so if we want to reach this 100 keV precision or better, with this shift of typically tens MeVs of a day, then we'll need a real-time monitoring, which would be really the way to improve on what was done at the lab time. And so for that, we need a tool. We need a tool to measure the energy, and the tool is called polarization. Actually, I tried to here sketch very quickly what was done again at lab. you have to see, and we will see in the next slide a bit more in detail why. You see on the plot on the right a measurement of the ratio of initial polarization of a beam and the final polarization of a beam as a function of a quantity which is called the magnet frequency, which is actually a frequency that is controlled on the magnet to actually change what we call the spin tune, so the precession frequency of the spin of particles that are stored that were stored in the lab or stored in a circular collider, if you want. So you take particles in a circular collider, you polarize them, and you let the spin precess, and then you modify this precession frequency by playing with the magnets or with a dipole. And by doing this, you are able to scan what we call resonance. And indeed, this is an effect that is well known in beam dynamics, even in absence of spin. We know that if a particle is oscillating, for instance, with given a specific frequency, which is an integer multiple, for instance, or half integer multiple, or fourth integer multiple of the revolution frequency around the accelerator, then with what we call resonance, the particle gets unstable and will be lost. And this is the same for the spin. If the spin's precession frequency is an integer multiple of the revolution frequency, or actually you have to combine all these revolution frequencies, so frequencies, betatron frequency, synchrotron frequency, and spin frequency, is an integer of the revolution frequency, then you match resonance, and you will lose the property. In here, you will use the spin. So you will depolarize the beam. And so this is what is observed in this curve, where you see the dots representing the measurement of the polarization as a function of time, which is a representation of the magnetic frequency. And you see that you with some depolarization at a given specific frequency. And precision of these measurements allow you to measure polarization, in turn frequency, and knowing frequency, you know the energy, because the spin tune here, the revolution frequency, is a product of A, which is the anomalous magnetic moments of the electron, and the boost, the Lorentz boost ratio of the beam, and the energy, and the electron mass. And so using this technique, we are able to convert a well-calibrated frequency scan in an RF element, something that we will know very well, into a very accurate energy measurements. And so again, to give an example of how it is going into this accelerator, you see here spin precession in an accelerator. The blue is a circular accelerator. The spin is the black vector and rotating around what we call the invariant spin field, which is a theoretical quantity, if you want, that is such that after a turn it goes back to the same vector. And so the spin oscillates. The spin of each particles in the accelerator oscillates around this invariant spin field. And what we'll call polarization is a statistical average on all the particles of the projection on the invariant spin field, and an average over the whole turn on the ring. We could use the fact that the particle spin naturally anti-aligns with the bending magnets in the circular accelerator. For that, this is just related to the fact that the synchrotron radiation is more likely with a spin flip in one direction than the other direction, as a sketch on the left. I won't go into the details. But this is not what we'll be able to do, because this time for the natural spin to build up, or the polarization of a beam to build up in a circular accelerator at the FCCee will be so long that we will not be able to use this to then polarize the beams, to then depolarize them to measure the energy. And here I've also sketched the so-called TBMT equation for the precession of the spin vector of a particle inside the accelerator, you see that this is something that that is depends on the transverse magnetic field, longitudinal magnetic fields, and also electric field present in the machine, which in first approximation is essentially related to the transverse magnetic field, and with this gamma A factor that is the spin tune that we discussed in the previous slide. Okay, so let's assume that we have a polarized beam. Now the question that we can ask is, do we have other sources for losing the polarization of the beam? And actually there are many, many sources for such depolarization. First, the synchrotron radiation process is a stochastic process and actually will smear the transverse momenta of the particle, which will also induce smearing in the orientation of the spin vectors of the particles, which in turn reduces slightly the average polarization of B. So we have to be careful about this effect. Also, the invariant spin field may depend on the energy. It is depending on the energy. Since it depends on the energy, it also smears the distribution, so reduces the average polarization. Another important effect, which is more technical, but still very important, is that any misalignments in the magnetic fields will also rotate this vector along the accelerator and reduces the average polarization of the beam. And last but not least, we'll have beam-beam interaction at the 4 collision points. And this beam-beam interaction will also induce very large fields, electromagnetic fields, in these places, which will also induce possibly depolarization. So there are many sources, and this is just an example here with the 2 curves that I show, just to get an idea, get a sense of how sensitive we are, for instance, for misalignment. So here, a colleague played with randomizing the alignments of magnetic elements in the FCCee ring. And so here, for 150 micron RMS misalignments, vertical misalignments, and 42 micron RMS misalignments. And you see what is the calculation obtained for the polarization of the beam, the maximum polarization that can be reached for a beam in such a ring as a function of the energy or the spin tune, which is the same. Gamma is the energy of the beam divided by the mass of the electron. And you see that what matters, so for some values of energy, you have very little polarization. This is the depolarization resonance that I mentioned before, and that you saw on the lab legacy plot. And you see that at 103.5, you are just in between 2 spin resonances, so you expect to maximize the spin about. And you see actually that the region energy, the width of the region of energy, where the polarization that you can get is relatively large, is very dependent on the amount of misalignments that you have, residual misalignments that you have in your accelerator. And you see that on the right, by dividing by 3, the spread in misalignments, you see that you have a much flatter region around the nominal beam energy, and a much wider range, which means that with a given energy spread of your beam, you will be able to reach a better average polarization. Another comment on these curves, because I think this is a nice way to see it. If you have a beam that has a very large energy spread that spans over several units of this spin tune, you can guess that the particles will cross depolarization resonance at a point or another. And indeed, the beam will depolarize, and this is exactly what is expected at the FCCee, which means that if we want to have a polarized beam in the FCCee, we should certainly not use beams that are colliding at the interaction point, because if you remember one of the slides when the performance plots of all the parameters for the FCCee, the spread in energy increases with beam-beam interaction at the interaction point, and increases by a certain amount a good factor, which means that those beams will have a too large energy period to be to exhibit a relatively large polarization in the FCCee. So we'll have to find a trick to do this technique of resonant depolarization and measurement of the energy. And polarization preservation is actually a very serious topic in those very high energy rings and colliders. And so the trick that we'll use is we'll use specific bunches injected in the accelerator, which we'll call pilot bunches, that will not collide with the opposite charge bunches. And so these pilot bunches will be specifically polarized, the polarization will be maintained, and will specifically depolarize those beams using a magnetic element to change the spin precession frequency. So we'll inject hundreds of those pilot bunches in the ring. We'll then switch on some wigglers. So these are to increase the amount of radiation that is emitted by these bunches, so that will reduce significantly the time it takes to polarize those beams in the accelerator. And typically we aim at reaching a 10% polarization in a couple of hours for those pilot bunches. Then we'll switch off the wigglers, and then we'll inject colliding bunches and operate the collider for tens or more of hours. And every 15 minutes, we aim at specifically depolarizing A pilot bunches to follow any change in energy in the ring. And this is both for the electron beam and for the positron beam. And so you have a sketch here of an example of a depolarizer, a strip line depolarizer, which is, if you want to picture it, it's two strip lines of conductive material that generates electric and B fields and magnetic fields in between. These plates are distanced by a couple of centimeters typically and are long for a couple of meters, say. And playing with the frequency of the electromagnetic fields that will inject in these strip lines, we can play with the spin tune. And on the left, you have an example of a simulation of what would happen at FCCee for at the energy for 45 GeV, which corresponds to center of mass energy, corresponds to the Z in the experiments. And you see a measurement of the exercise of measurement of the polarization as a function of this of the detuning of the depolarizer, which means of the spin precession frequency. And you see that you can cross zero. And actually, if you do it fast enough, then you can not stay at zero, but cross zero. So this is interesting because this means that this beam can then, this bunch can then be reused again later on to do again this very same exercise of trying to measure the depolarization frequency, because the point here it's set at zero, corresponds to spin precession frequency, which in turn corresponds to an energy measurement. And so we are able to depolarize a single pilot bunch at a time, maybe not fully depolarize, so we can reuse it several times, which would be great. Another example here, this is just different plots, but at the WW threshold, so it's 80 GeV beam, and we see that we are still able to do so in the FCC ring, because the FCC ring is much larger than the lap, so 91 kilometer circumference compared to the 20 and so kilometers of the lap. And this is a place where we'll have the unique ability for a very, very high precision W mass measurements and with measurements, which is of interest. So I said, oh, we depolarize the beam. I said, but I didn't say, oh, we measure the polarization. And for the measurements of the polarization, we'll use Compton scattering, which is a QED process, so very well controlled process. and for which we'll ask to measure the vertical beam polarization, allowing to make a scan of this this precession frequency in a few minutes, so that we have a quick measurements and quick and precise measurements of the polarization and in turn of the beam energy. So this is an example here of the differential cross-section for the Compton scattering as a function of the energy of photons that are scattered in the process. So this is outgoing photons in these diagrams. And for instance, you can look at the blue curves. You have the cross-section for three different value of the polarization of the beam for vanishing polarization, longitudinal polarization, for instance, of the electron beam, which is in the middle, or for opposite signed polarization of the beam. So this is just an example for the longitudinal polarization, just to sketch that. The Compton scattering is sensitive to polarization of the electron beam. It's actually also sensitive to polarization of the laser beam. This is maybe one of the only formulas that I will show today. This is, again, the differential cross-section for Compton scattering as a function of Y, which is basically the energy of the scattered photon scaled by the energy of the incoming electron. And as a function of an angle in the observation plane, this is azimuthal angle in the observation plane of the photons. And this cross-section depends on the parameter, which is the Lorentz invariance, which is basically the product of the incoming beam energies and the crossing angle alpha. So you see that this differential cross-section exhibits several terms. In blue, there is a term that is basically independent on the electron beam polarization. It contains itself two terms. The first one, which is unpolarized. The second one, which is proportional to the linear polarization of the laser that you would like to set to 0 because it's useless to have it. It's a nuisance parameter. And the second part, the green part of the formula, contains the electron beam polarization dependent terms, which are proportional to the circular laser polarization. So you would like to have a fully circularly polarized laser. I'm already using the word laser because you would like to have a lot of photons in initial state to have a lot of or enough photons and electrons scattered to be measured. And this is proportional to, then you have two terms, one which is proportional to the transverse polarization, which is of interest for transverse polarization of the electron beam, which is of interest for the resonant depolarization technique to measure the electron beam energy and positron beam energy. And another term which is proportional to the longitudinal polarization of the electron and positron beam, which will have to some extent, because there will be a spin precession, so there will be some residual, probably some residual linear longitudinal polarization of the electron and positron beams, pilot bunches that we would like to diagnose. Okay, so this means one thing. So we'd like to be sensitive to the term that is in cosinus of those angles, phi. So this phi is the observation angle in the azimuthal plane, and so azimuthal angle in the observation plane. Sorry, and phi like is the orientation of the polarization of the electron beam, which is nominally vertical, let's say. And so we'd like to be sensitive to this term. So we'll have to have a fully circular laser, polarized laser, and we'll need to control this polarization, because any mistake on this would induce a mistake on the measurement of the polarization, or any variation of the circular laser polarization with time would induce a systematic on the determination of the polarization and the energy of the electron beam. So a precise control and monitoring is required there, which involves some technological developments that are ongoing. Compton scattering is also a very clean process. This is why we are using it as a candle to measure the polarization of high energy electron beams. Typically at 45 GeV, sorry, QED corrections to the bond level cross section that I mentioned before amounts to typically per mil on the term that is sensitive to polarization. So this generates change of the asymmetries that we will measure. So if we measure left-right asymmetries, this will induce a change of the order of 1 per mil, which is quite small, but still may need to be taken into account if you want to go for very accurate Compton scattering measurements. And this is how the Compton polarimeter look like. So we'll have a laser interacting with electrons and positrons in this yellow region. Electrons, positrons will be deflected by a, not field, it's a field, a dipole, the dipolar B field, magnetic field. And scattered photons will go straight in the direction of the incoming electron or positron beam into a detector that is placed here, sketched in yellow and with a green dot. While the scattered electrons will have lost energy, so will be also deflected by the B fields, but much more than the nominal electron beam. And so scattered electrons will be located in an ellipse in a detector that will be placed about 200 meters away from the interaction point and the magnetic field. And so by measuring both photons and electrons distributions, we'll be able to measure the transverse polarization of the electron beam. And so if you remember, this is we are going to look at distributions that are phi dependent. So we'll have to measure really transverse distributions of this electron beam, and not only distributions, and especially vertical distributions on the electron and photon, scattered photons, and not only on the horizontal axis. Another a very good point of the concept that has been proposed by Nikolai Mushnoy several years ago in this context is that by measuring photons and electrons at the same time, we'll be able to measure all the polarization parameters, including the nuisance parameter from the laser, which is interesting to control the systematics further. And at the same time, by measuring the position of the photon beam and the position of the parameters of the ellipse for the electron beam, we'll be able to, by making differences in this position, we'll be able to measure the ratio of the integrated B fields and the initial electron beam energy, and the product of the integrated B fields and the initial photon energy. And by doing the ratio of these two quantities, then we see that knowing the wavelength of the laser or the energy of the photons in the initial state, which is the same, to a good precision, then we'll be able to measure the electron beam energy with a good precision also, just by measuring those positions. So the Compton polarimeter itself, even though it is not designed to do measurement of the energy, direct measurement of the energy, will be able to do this measurement of the energy by measuring the position of this. And we'll see that even though this is with much less precision than what is targeted with the horizontal depolarization, will be an interesting tool in some cases. And so this is a sketch. I won't comment everything here. This is just a sketch of all look like those distributions. And so on the top, you see top left, you see the photon distribution. So you have a nice spot of photons that will be measured by the detector. And on the left, as I said, you have an ellipse shaped for the electrons, and where you see that the electrons are mostly located on the borders of these plots, which make these measurements relatively difficult. Also a comment, you see the size of the beams on this picture. This is typically 1 or 2 millimeter transverse size distribution. So we'll need to measure the vertical distributions in those plots with typically tens or few tens of micron precision, the position of electrons and photons, which poses some nice challenges in terms of detection and on resolution of the detectors. And so typically we have shown that in a few seconds for the parallel benches at FCCee, we'll be able to measure with statistical precision of 1 per mil all the polarization parameters, and we'll be able to measure the beam energy with typically MEV accuracy, which is totally complementary to the horizontal depolarization technique. So we have calibrated the beam energy, but the beam energy is not the center of mass energy at the collision points. Indeed, you have a crossing angle. And so the energy, the center of mass energy is basically the square root product of the beam's energies, the product of the beam energies, and the cosine of the crossing angle aft. You will have first to measure this crossing angle, which you can do with muon pairs. So this is on the bottom left. This is a sketch of what has been suggested to do at FCCee. And you see for the blue curve, this is taking into account most of the effects, namely initial state radiation and resolution of the detectors, and a possible asymmetry in the beam energies that has been injected, just to check that the procedure is able to extract the crossing angle properly, which is the case. You have other effects that will appear at the interaction points, and one of them is beam effects and interaction point. Beam effects, which means that fields will be seen by both beams coming from the other one, and these fields will change the crossing angle and will change the energy of the colliding beams. And by measuring the energy spreads and using, again, dimuon events, we are able to measure energy spreads and an asymmetry in the beam energies, which, with this information, the measurement of the crossing angle and the knowing of the beam's energy itself before they interact, will be able to measure and calibrate with good precision the center of mass energy. Another point that must be said, and this means that we need to have good control on the accelerator itself, is that electrons will travel in the accelerator in between the polarimeters, where the beam energy will be measured, the polarization will be measured, and the depolarizers, where the beam energy is measured, and the collision points, which means that we have to take into account for synchrotron radiation that is happening in between those points, and we'll have to correct for that, and we'll have to have good models. And the time that we take to calibrate and understand all these effects in detail with the needed accuracy will take some time. So I've mentioned measurements at the Z, measurement at the W, where we'll be able to employ the resonance depolarization technique. We'll also would like to operate at high energies, like at the Higgs energy, at the Higgs center of mass energy, so that we can measure the electron Yukawa. There, this would be very important to be able to have a very small energy spread of the colliding beams. So monochromization will be important. Knowledge, precise knowledge of the center of mass energy will be important. And will not be able, unfortunately, to operate resonant depolarization at this technique. So this is where direct measurements of the beam energy with the Compton scattering experiments will be useful. And this is also where a very reliable energy model, so a very good knowledge of the accelerator, is important. Of course, we could also apply the same techniques at the X-Strahlung, and also use recoil of the Z-peaks to calibrate in real time the detectors, and at the same time the center of mass energy. Use also radiative events to measure the Z mass in real time at high energies, to in turn calibrate the center of mass energy. This will be also used at the top threshold to measure the top mass, the top width, with a few about 10 MeV, 10 to 20 MeV precision for the top mass. And so a center of mass energy here, if we want to keep in mind the picture, a figure, the center of mass energy at 10 MeV per point will induce an uncertainty of 3 MeV on the top pass, which will be sufficient. So a good, relatively good energy modeling is necessary, and will be helpful. So as a summary, I've sketched quickly what is the phase scope of the FCCee. It covers from the Z to the top pairs. And this exciting physics potential requires impressive improvements on beam energy calibration compared to what has been done at lab. And this beam energy calibration will be made thanks to very tricky techniques using spin precession frequency, measurement of polarization in real time in the accelerator, which poses some challenges also in terms of operation of these systems. And so telling that we'll reach this precision at FCCee is not just a simple word. This implies a lot of work and a lot of techniques to be employed and challenges to be faced in the coming future. But of course, the largest challenges will be operating those systems in real time. If you want more information, you can look at the FCCee CDR, the midterm report that has been published, but only to the CERN community so far, and the EPOL group reports at yearly FCCee weeks that are, I think, public. Thank you very much for your attention.
Super. Thank you very much for the very nice talk. This is a very uncommon talk. We have never had this kind of topics discussed on the webinars. So it's very nice to have insight on this kind of details. So I have a couple of questions, but I don't know if Roberto would like to begin, or maybe.
Yeah, it was very nice, the questions, Aurélien. I mean, the webinar. It was, as Joel said, it's very impressive. I mean, things that we used to not think about. I mean, from the side of the theoretician, like how complicated it is to really be sure that the center of mass energy is the real center of mass energy, the one that we put in the calculations. Yeah, but for the point of, I mean, I was wondering because a lot of the webinar you explain a lot of the importance of the polarization of the electron beams I mean, to control this, because it can give you more information about the process. So, but how, one question more or less related with why it was too complicated to do the same polarization studies in the previous accelerator, let's say. I mean, now of course we have better technology to control better the variables, but at the level of lab was, because usually all the studies were unpolarized beams. I mean, I know that now this is I guess it's better, it's easier, more energy. The processes would be more important for the study of new physics, or to establish how well is the standard model. But was that kind of, I mean, if you can comment on that.
Yeah, it's not clear to me if your question relates to the use of polarized beams for physics, or the use of polarization for the beam energy measurements. Actually, for the beam energy measurement, this has been employed at the lab time. I mean, this has been used. But the difficulty there is that the need of this technique was not so much foreseen at the time. And so what were people doing is that they had colliding bunches in the accelerator at the lab time, doing physics for tens of hours. And at the same time, from time to time, when the conditions were allowing it, meaning that the beam were not just lost in the accelerator, and they were able to keep one of the two beams for some time in the lab vacuum tube, they were doing this resonant depolarization technique on electrons and then on positrons. But they could not do at the same time, because actually lab time, it was a single tube where both electrons and positrons were circulating. And so you had to also cut the collisions at the same time. So this is one of the main difficulties for lab. Now we learn from that, and we plan from the beginning that we need to use this resonant depolarization technique. And so that's why we'll inject pilot bunches specifically dedicated for that physics, for these measurements of energy. If your question is more related to the use of colliding polarized beams for physics, I think the main difficulty is that the higher the energy, And typically, the more difficult is to have polarized high energy electron beams in colliders. And this is a study that has not been that is not being pursued at FCCee because it's considered as too complicated. On the other hand, at the CEPC, the Chinese project, they considering this as an option to have polarized electron beams, a serious option to have polarized electron beams in the accelerator and polarized positron beams in the accelerator to collide longitudinally polarized electron and positron beams in the experiments to, for instance, enhance some standard model cross sections amplitudes, or decrease some background amplitudes, and be more sensitive also for some process of new physics, for instance. I hope I answer your question as you would like.
No, yeah. Yeah, it answered my question. Thanks.
So this is very interesting, no? Because what I understood is that initially you inject these pilot waves, but to polarize them, these pilot beams, but to polarize them, it takes like, they're 2 hours, right? So then you have the bunches there for 2 hours, and then afterwards, once they're polarized, you start injecting non-polarized
That's right.
bunches, right? So what I'm just wondering is that if there is any advantage in polarizing the bunches for physics to a degree of 10%, because if you want to polarize them more, then you need much more time than 2 hours, right? That's what I understood from at some point that you were showing the animation, that it took too much time not to get an efficient polarization.
The difficulty, so let's look at this. The difficulty with the colliding bunches, maybe I could go back to one of the first slides. The difficulty with the colliding bunches is that here you have, for instance, the quantity which is named RMS bunch length. So this is the length of the bunch in the longitudinal direction. And you have two numbers. The first number is with synchrotron radiation only. And then the second number is when you also include in the calculation the fact that you have what we call Beamstrahlung, which is the fact that you have another colliding bunch coming from the positron beam at the interaction point, if you're interested in the electron beam. And these the very high electromagnetic fields that are created by this counter-propagating oppositely charged beam actually modifies the dynamics of the particles in the accelerator. This is if you can think of it as a pneumatic element in your accelerator. This is a very strong one. And these very strong magnetic elements will induce radiation, and very strong radiation. We call them Beamstrahlung photons, and we'll have a huge amount of power generated by this, and managing this is an issue. And this will also increase the energy spread significantly by more than a factor of 3, typically, the energy spread of the beam. If you increase the energy spread of the beam, and you go back to this picture, when you see, for instance, on the, let's look at the right, and you see two strong resonances around 1.1, so 103 and 104, which corresponds to two specific spin tune values separated by an integer, which correspond to strong spin resonances. And then you would overlap the energy spread of the beam. And the spin resonances, this is A gamma, so G minus 2/2, so the anomalous magnetic moment, times the energy of the beam, the Lorentz boost, okay? And so if you overlap here the energy spread of the beam, you would see that the energy spread of the beam would not fit into this simple curve of a change of one integer in the spin tune, which means that your particles in the bunch, the colliding bunches, will go through from time to time those resonances and will lose. And so the coherency of the spin orientation of the whole bunch will be lost. And so that's why we do not plan to have polarized colliding bunches, because we think that this is extremely difficult.
Mm-hmm.
So the technique that is used at CEPC, where they want to do this, is what they do. This is a very tricky technique. They polarize the electron beam first. They accelerate the polarized electron beams. They inject the polarized electron beams in a circular accelerator. They increase the energy of this electron beam in the circular accelerator while preserving the polarization, which is a totally new topic in accelerator physics and extremely challenging. They designed it specifically for that. And then they inject this very high polarized electron beams in the accelerator. But then this is not the end of the story, because then you inject vertically polarized electron beams and positron beams. And then you have to rotate the polarization of the electron and positron beams towards longitudinal, because the physics is more about longitudinally polarized beams at the interaction point. Okay, so this is LACT, right? So this means that they have to make very specific arrangements in the accelerator to do so. And they will inject as FCCE, but they will refresh electron beams and positron beams all the time. And refreshing the electron beam and positron beams all the time will allow them, I think they are allowed to keep, to preserve relatively high polarization of the electron-positron beams in this accelerator. But this is uncharted territory also, and this is extremely difficult, and this is a strategy that has not been pursued at FCCE.
I see. And this technique that you use, using Compton scattering to measure the polarization. So this is this being carried out someplace, being tested? Is this well known, or is this currently under evaluation before being implemented at the FCCee?
Well, the Compton scattering is well known. I mean, this is Compton scattering for measurement of polarization has been used since many years. Actually, I mean, in the place where for the first time beam polarization has been shown in accelerator was in ERA in Tessy, in Germany, in Hamburg.
I see.
And there they used Compton scattering to demonstrate that actually we're able to build up polarization with time, and they had very groundbreaking results at the time. And this is now, Compton scattering is a customary technique to measure polarization of beams in the accelerator. This is not the only technique. There is also another technique that is very convenient and actually that is used in synchrotron radiation accelerators, which is using the lifetime of the beam. So what we call the two-check lifetime, so which is related to interactions in between electrons in a bunch. The cross section depends on polarization and actually on the square of the scalar product of the polarization or the spin of the two particles. So in average, this is the squared of the polarization vector, magnitude of the polarization vector of the beam that matters. And having polarized beam changes the lifetime of the beam. And so by measuring lifetime of the beam, which is a measurement that you do all the time because you measure the charge of the beam or the currents in your machine all the time, then you can measure the lifetime, then you can measure the polarization. But you don't know its orientation, you don't know its sign, you just know its magnitude. And here, we would like to measure precisely its vertical component.
And this measurement doesn't give you something like the Beamstrahlung, right? It doesn't give you feedback into the at the collision point.
No. No.
This is done like far away.
Yeah.
far
Yeah. This is done kilometers away from the interaction points.
Okay. So where exactly? Because sorry, Roberto, that I'm taking up all the time in questions. But so on one of your first slides, you showed you know it was on slide 3, I think, that you had your PA, PB, right? So there you see like PD. I assume that's where one collision point would happen in PG, in PJ, right? I guess that's where one of the experiments would be positioned. So I imagine that in one of the other PHs or PFs you would have this measurement. Where would that happen?
This is okay. To be honest, I mean, this is something that we are still that is still under discussion. Where to locate these experiments. So yeah, indeed, PA, PD, PG, PG, PJ are the location of the 4 experiments that are planned. Now, actually, the compound polarimeter doesn't to some extent doesn't matter much where you place it, because you want to measure the beam energy at one point, and then you extrapolate to get the energy in different points. This is also why it's very interesting to have several experiments, because if you don't do things perfectly, then you won't have the same Z mass at the 4 different experiments. And this is exactly what happened at the beginning of the lab. But there is basically 2 things that must be considered. On one hand, operational aspects, cost, and so on. So saying, if you want to simplify the things, you would say, I want 1 polarimeter per beam, and I will place it where it's easier to place. On the other hand, if you think about very high precision, uncharted territories in terms of precision, systematic uncertainties, and you want to maximize your knowledge of a machine, I would rather say better place 1 compound polarimeter close to each of experiments and for each beam, which clearly multiplies by 4 the work to be done. But then there is also some place close to the experiments, just after the straight line from the experiments. There is a place where we could place the compound polarimeters. So this is a very interesting place. And this is a very interesting place because it's close to the experiment, so we minimize the systematics. And there is also another aspect that I didn't discuss. But if we want to measure the very high precision, like 10 to the minus 4, 10 to the minus 5 precision, the electroweak asymmetries, for instance. Electroweak asymmetries are sensitive to longitudinal polarization of the beams, of the colliding beams. Even though I said, in principle, they should not be polarized, we need to control this polarization at the basically same level or to a factor 10 compared to the asymmetries, the precision you want on the asymmetries. You need to control the longitudinal polarization of both beams independently at the same level. So typically, you will need to measure those polarization to the 10 to the minus 4 level. And in that case, yeah, and this is the one tricky thing. You have arguments to say that you cannot build up longitudinal polarization at a certain level, but you would like to make sure that you are down to this level. And even though you can say, you can have arguments saying, okay, my vertical polarization is not larger than that, so I know that with spin precession, I cannot have a longitudinal polarization larger than this. It would be also interesting to have a direct measurement of the longitudinal polarization close to the interaction points. And if possible, to such an accuracy, which is a huge task. That's true. That's totally uncharted territory in terms of compound backscattering, because those experiments typically reach the Fermi level. This will need to account for QED corrections and so on. So this is a huge effort. But this may be also a very interesting thing to do if we want to have another cross check on such a systematic uncertainty that will be totally limiting the measurement of the asymmetries if we don't control it. And the point is that you have no physics process that I know. Maybe there are, but I don't know. I cannot think of a physics process that is independently sensitive of the electron beam polarization and the positron polarization, longitudinal polarization, with a precision that would allow us to have a control on the asymmetries, which then gets very tricky. And similarly, you could use, for instance, azimuthal asymmetries in detectors to measure the transverse polarizations. But again, you are sensitive to the product of transverse polarization of the colliding beams and not independently. And what matters for the asymmetries in independent polarization of both beams. So location is a discussion. Number of polarimeters also is under discussion. Today, the baseline is to have one polarimeter for the whole machine, probably placed close to the IP of one of those experiments, which would allow to perform those cross-check that I mentioned, at least in one experiment.
I see. Okay, let's see if there's any questions. Okay, there's a viewer thanking for the presentation. I don't know if Roberto, you have another question?
Yeah, I have a doubt. Yes, I have a question, a doubt. I mean, maybe off topic, but related with this, in the sense, because as Joel asked before, to have these polarized bunches going around the FCCee, you need more or less 2 hours to have the right amount of polarization. This is the reason, or it's not possible to do the same study in the case of linear colliders? I mean, because I guess in a linear collider is too short, the path for so there is no time to polarize the beam, or it's different, completely different the scenario because the beam is not going around the accelerator, let's say.
Yeah, exactly.
I mean, compared to the FCCee with maybe with a linear collider.
So yeah, it's a totally different topic for the linear colliders. So the specificity of FCCee on circular colliders in general is that the beam is living in the machine for a long time. So here the topic is mainly following any change of energy during time that is induced by spurious effects like tidal and leakage currents or whatever, or any new effect that we'll discover in FCCee. For the linear colliders, I mean, polarizing the beams is definitely an asset compared to circular colliders, because in principle, since it's a linear collider, you don't have cumulative effects that you observe in circular colliders, so you can more easily transport large beam polarization from production to collision points, and after the collision points, the beam are dumped, so they go to the trash. So this is not an issue. This is planned to have 70% or more electron beam polarization at the interaction points. There will be some Compton polarimeters to measure this quantity, the level of polarization in real time, and optimize for the machine in a region where we can minimize the systematic uncertainties related to the beam transport from the Compton polarimeter location to the interaction point location. There will be another aspect that will be indeed related to beam depolarization at the collision point due to the beam effects, again, those guys, that will appear in the IRC or CLIC or any linear collider experiments. And that will be even more important. And also that's why there will be also a diagnostic of the beam polarization after the collision before it is dumped. And so the collection of all this information will allow us to calibrate with high precision the polarization interaction points. And this will be complemented by physics measurements, for instance, using W pairs or Ws at the interaction points. To have also another measurement of the polarization with the data itself in the experiments, but on a very long time. Polarizing the positron beam would in principle be possible, but this is a very challenging topic because you need a very high charge, a very high current of polarized positrons. So even though generating a large amount of positrons is possible, polarizing them is complicated. So what you need is you need to produce polarized positrons. And to produce polarized positrons, you need to basically shoot photons on a target and shoot the circularly polarized photons on the target. And to produce a very large amount of polarized positrons, then you need a huge amount of polarized photons that need to shoot the target that will heat up in return because there will be absorption there. And so this is maybe where the challenges, the technical challenges lie in the linear colliders, is how to produce this copious amount of polarized positrons for collisions. And so that's why now the baseline for the ILC is rather to only polarize the electron beam, and an option of an upgrade to polarize also the positron beam, which is much more difficult. But then there is no point in measuring in real time the energy because basically it's a linear collider. So you inject, you accelerate, and you collide.
Okay, so we need to go. We've been past the hour, and I have this room reserved for 3 more minutes. So so we need to finish now. So thank you very much, Aurélien, because it's been great. It's been very interesting to find out these things that we usually, when we do particle physics, we don't really think of, right? So thank you once again. I'd like to remind everybody to please stay tuned. In 2 weeks' time, we will have Delia Portillo, who is from Atlas, giving also another webinar. So that's it from us. And
thank you very much
for
the invitation.
No, thank you. Well, I will be seeing you around. Take care.